Well, why don't we go ahead and get started? First of all, welcome to everyone that's joining us for today's What's on the Moon webinar. We are thrilled to be able to introduce you to the winning teams of Phase 1 of NASA's What's on the Moon Challenge. We're going to kick it off with some introductions, and then we will move into a brief overview of the What's on the Moon Challenge for anyone who's unfamiliar with it. And finally, we'll save most of today's time to hear directly from the winners themselves. Let's kick it off with some introductions. My name is Kyla Jeffrey. I am the VP of Customer Success at HeroX, and I've been working with the NASA Centennial Challenges team to administer the What's on the Moon Challenge. I am thrilled to have with me today Denise Morris from NASA. Denise, I will pass it over to you.
Hi, everyone, and welcome. We're glad to have you. My name is Denise Morris. I work at NASA at Marshall Space Flight Center in Huntsville, Alabama, and I am the Centennial Challenge Deputy Program Manager and the What's on the Moon Challenge Manager. So glad to have you all, and I will pass it over to our head judge, Darren Malott.
Yes, thank you. My name is Darren Malott, as she just said, and I work for Department of Energy. Actually, I manage, or I'm director of the Exploratory Research and Innovation Center there in the Office of Fossil Energy and Carbon Management. And my role basically there is to look beyond the R&D efforts that people are currently working on and look for these paradigm shifting kind of technologies, which is why I'm so pleased to be a part of this and seeing what these teams have done. And I guess, who am I handing it to now? Okay,
let's hand it to the Astrobotic team.
Perfect. Hi, everyone. I'm Mike Provenzano. I work at Astrobotic. I lead the Planetary Mobility Department. We're really excited to be here today and share more about our solution with you, and happy to answer some questions. And I'll hand it over to Troy on our team.
Yeah, thanks. I'm Troy Arbuckle. I'm the lead mechanical engineer for the Planetary Mobility Group. Mike is directing the group I work for at Astrobotic, and I suppose that's sufficient. We're working on some really exciting rovers and infrastructure components. We're really excited to be here today.
Awesome. We are thrilled to have you here. Next up, let's move over to the Planetary Surface Technology Development Lab. Paul, I'll pass it to you.
Thank you, Kyla. Yeah, thrilled to be here. So I'm in Michigan Technological University. I'm an assistant professor there, and as part of the mechanical engineering department, we have founded a lab which is called the Planetary Surface Technology Development Lab, and we have quite a few students working in that lab, but the ones that have really played a key role in the What's on the Moon Challenge are listed here. Travis Ververnick, Eric Van Horn, Marcella Guadagno, who is with us here today, Colin Miller, and Hunter McGillivray. And so we're very happy to be able to share this win with everyone. It's very exciting for us.
Great. Thank you so much, Paul. Marcello, I'll pass it to you to introduce yourself.
Hi there. I'm Marcello. I work with Paul. I'm a graduate student in the same lab as him, and I do quite a few different things there.
Great, thanks, Marcello. Next up, last but not least, our Mission Activity 3 winners, SkyCorp Incorporated. Dennis, over to you.
Well, thanks. Proud, happy, and thrilled to be here today with everyone. Unfortunately, the rest of our team is hard at work. We have a NASA Phase 2 safety delivery today, but we're very happy to be here, and been a long time lunatic in this area.
Awesome. Thrilled to have you. Thank you so much, Dennis. Next up, I'm going to pass it over to Denise Morris. And Denise, why don't you tell us a little bit more about the What's on the Moon Challenge for anyone that might not be familiar with it?
Okay, sure, Kyla. For the audience, I know all the winners are very familiar with this challenge, but what we're seeking is to incentivize flexible, robust energy distribution management. So Phase 1 of What's on the Moon opened in September of 2020. We closed this year in March of 2021, and we asked the teams for a concept design for power distribution and energy storage on the lunar surface. We received about 60 submissions, with 43 being eligible across 3 tracks that represented 3 hypothetical mission activities. So on May 20th, it was a special day. We announced 7 winners. We awarded the first three, the grand prize winners, $100,000 each, and then we had four other winners that we gave $50,000 each to, for a total of our $500,000. So back to Kyla for our video.
On Earth, we can light the darkness, power our lives, supply energy for the world's needs. On the moon, we cannot, or at least not yet. With 350 hours of total darkness and day after day of sub-zero temperatures, traditional Earth-based power storage and distribution technologies aren't going to be enough. Future lunar explorers will need power to use the tools and technologies necessary for uninterrupted exploration and survival on a new world. That's why NASA is searching for solutions beyond our ongoing research. From garage inventors to small businesses, industry, and university students, NASA's Watts on the Moon Centennial Challenge is crowdsourcing ideas to solve the difficult tasks of power distribution, storage, and management on the lunar surface, and enhance these technologies here on Earth. As NASA builds a sustainable human presence on the moon, continuous energy will be a critical piece of this puzzle, so that one day we can light the darkness on the moon.
Great. Thank you so much for that introduction, Denise. And I have to say, it's so fun to watch that video again, now that we have the winners in front of us, and just really thrilled to be able to hear from you all today. Denise, a question for you. Can you tell us about why this issue is so important to NASA, and why did you turn to crowdsourcing for potential solutions?
Sure. The Watts on the Moon Challenge is a very important challenge to NASA, because when we go back to the moon for long-term sustainability, we're going to have an infrastructure. And as we all know, one of the most important pieces of that infrastructure will be the power. The power would be used for many things, like building roads, habitats, telecommunications, etc. And it's essential for the long-term human habitation anywhere we go. So yeah, we're excited to do this. And for the crowdsourcing piece, Kyla, it was important to get ideas from the community, because they have unique technologies that help incentivize us on getting back to the moon. NASA's developed ways to generate the power, with Glenn Research Center being the lead for that, but we needed help for the distribution and the storage of the power. So when we use crowdsourcing, we involve the public in helping us figure out the hard problems. They have amazing ideas. We're always excited to see what they come up with. And today will be a great example of this by showcasing the three grand prize winners of Watts on the Moon, phase 1. I'll talk a little bit more about phase 2 later, but that's what's important to us, and crowdsourcing really works for these kind of activities.
Great, thanks, Denise. You touched on something that I want to call out and highlight, and that's that we have 3 grand prize winners, but we also have 4 winners. And I just wanted to take a moment for us all to acknowledge the 4 winners who also received a prize. These 4 teams received a $50,000 prize. We have Team Astrolight out of Rochester, New York, KC Space Pirates out of Kansas City, Missouri, Moonlight from the University of California, Santa Barbara, and Team Fuel Pod out of Johnston, Colorado. And it's just a true testament to the quality and caliber of these submissions as to how difficult it was to choose those 4 winners and the 3 grand prize winners. And so I'll extend my final shout out to everyone who submitted but wasn't recognized as a winner. It really was a very tough decision for the judging panels to get to this point. Next up, I am going to pass it over to Darren to introduce the first winning team. So Darren, over to you.
Okay, great. So the first winning team is Astrobotic. They were awarded the grand prize in Mission Area 1, which was delivering power from the power plant to mobility platform inside the crater. So Mike and Troy, I'm gonna, without any ado at all, I'm gonna hand it over to you guys for the presentation.
Thank you, Darren. I appreciate that. So I'll talk to our slides today. I'm the director of our team, and then we have Troy on the line, who's our mechanical lead. Also want to give a shout out to our other teammates who aren't here right now, but John Thornton's our CEO, and he's also the team lead of our AMP team. Tom Oberst is our architecture lead, the one that was facilitating kind of all the designs and concepts. Lance Redu is our electrical lead, and then we have our systems engineer, Joe, and Andrea Davis, who is our mechanical engineer on our team. So a lot of really diverse backgrounds that are contributing to this team, and it's been really exciting to put together this architecture. We can go to the next slide. So yeah, I commend NASA for kind of having this approach where they go out to different companies and ask for the best solutions. NASA's already funded Astrobotic. We're really happy to say that we've been working on things like rovers, wireless charging systems, our vertical solar array technologies, all funded under different NASA research and development programs. So what I'll mention is I'm going to give an overview of each of the technologies that comprise our system, and then I'm going to tell you a little bit about how the whole system works on the next slide. But for now, so we have our cube rovers, which are small to medium-sized rovers. They're the ways that we distribute power on the surface. So ultimately, the mission begins when our VSAT is flown on a lunar lander to the moon. The VSAT's deployed off the lander. And then once it's deployed in its location, we have rovers that can drop down, deploy from the VSAT, and drive off and extend cables to different locations. And essentially the rovers are cabled to the VSAT. They're connected through a physical connection. And then we have wireless chargers that are mounted on the rovers. And that allows the system to be portable, flexible, so it can drive to locations like the permanently shadowed regions that we hear about, and they're so difficult to figure out how to get power to. So in this case of an excavation rover, that is really, really useful because you can have a rover that drives off, collects some lunar regolith or sand, and then comes back, receives power, and that can all be in a permanently shadowed region without ever having to leave. Which really increases the operational lifetime of the system that's performing in the permanently shadowed region. So we have our rovers right now that are funded under a NASA tipping point contract. We have our wireless charging system in partnership with our manufacturing partner called Wybotic. That's also funded under a tipping point contract. We have our vertical solar array technology, which is a recent announcement that we're thrilled to be working on. That's essentially a 30-foot tall solar array that can be deployed at the lunar pole and receive light and power systems. We are partnered with Honeybee Robotics and Altia Space to develop the cable reel systems and the connectors. So one really cool part about this architecture is that the rovers not only can have wireless chargers on them, but they can also have interfaces that allow them to mate with things like the water production facility or an oxygen production facility. So it's really scalable to support lots of different architectures. And then the best part about it is it can all be delivered on a single lander. And Astrobotic is in the business of making lunar landers. So we could deliver this end-to-end mission in one flight to the moon. You could go to the next slide, please. This is our last slide. So it kind of gives an overview from the top down of how an architecture like this would work. So I had mentioned before that the VSAT gets delivered. You can see the lander in the bottom. When the VSAT is deployed at its location, the plan is to deploy it on the crater rim so that it always has access to sunlight. And when that has access to sunlight, that can continuously generate power for the other assets that need to receive it, whether it's inside of the crater or outside of the crater. And as I mentioned before, so the wireless chargers allow us to drive in the crater and power things like a rover that is driving back and forth and needs to just receive power without mating. And that is really helpful because the dust on the moon is really challenging. If you try to mate connections physically, then there's a big risk of dust interfering with the actual connection. So wireless charging makes things way simpler, and you're able to dock with it easier too. And then it also has the alternative connection, which I just mentioned on the slide before, where we could drive up next to an oxygen production facility or a water production facility. And then you can actually plug in with our electrical mating mechanisms that would be developed by Altius, and you can just straight up transfer power through the cables right to those production facilities. So We have different scale rovers that can do those different activities, but overall, that's the architecture in a nutshell. Happy to answer any questions later on.
Okay. Well, then maybe I'll ask you a few questions since you're happy to answer them. This is great.
Sure.
No, anyway, that's very interesting way you're trying to do that. So first, just a curiosity, have you participated in a Centennial Challenge before, your team?
No, this is our first one, and it was really exciting. I mean, it's different from our process of normally what we propose to NASA proposals, in that this was all the work that we did, and it's combining all of our other efforts together to try to go after a bigger opportunity, something that NASA sees as something that's really useful, and we see it actually as not just a step to get to the future, but this is the thing that will hopefully be the seed for actually having a lunar infrastructure on the moon, a lunar power infrastructure on the moon. And that's really what our company stands for, is create a robotic infrastructure on the moon.
I think this opportunity was really great because we all kind of had in the back of our minds what the end goal should be. And we've been working to that piece by piece, step at a time. But this opportunity allowed us to formalize those ideas, get them in front of a different group of people. And it allowed us to work out some bugs that maybe, the back of our mind, we didn't have a solution for. But I think that really brought a lot together for us to think about it in this context.
Excellent. Well, then with that said, then what would you advise someone considering participating in a challenge like this? Any recommendations after you've been through this process now?
Yeah, definitely. I think it's most important to understand the problem statement really well before jumping in and proposing a solution. That process allowed us to kind of understand what technologies we should leverage from Astrobotic, and that then allowed us to pick the technologies that are reliable and have high maturity to actually meet the problem statement, but also offer kind of a novel piece in how we approached it from our own side. So I think generally there's a reason why NASA is asking for teams to say, the state of the art right now isn't sufficient. We're looking for something else that's better and can bring more capabilities to all those that use this kind of stuff on the moon. And it's important for the team to understand where those weaknesses are in the state of the art. And that will ultimately, hopefully, bring some clarity into the gap and allow you, if you're proposing to opportunities like this, to figure out how to be different and how to win something like that.
So you touched on this before, but I think I have time for another one. But I'm curious, what do you see as the next steps for your technology?
Yeah, so I'll talk to this, and Troy, if you have anything to add, feel free. We are actively flight qualifying many of these systems under different contracts. So the goal right now is to continue that flight qualification campaign and make sure that these technologies will work on the moon. But now the next step is after this competition, it gives us the funds, the resources to go out and actually put together a full end-to-end demonstration. And that's what we intend to do with this. So over the next couple of months, the goal is to actually show a working demonstration of all these technologies together. And then once they're proven to survive the lunar environment, then the next step is just to fly them there.
Mm-hmm. And I think
Easier said than
interestingly, yeah, I think interestingly, you mentioned that the VSAT, the vertical solar panel, was kind of the core of this infrastructure, and that's one of our main targets. So we'll be developing that over the course of a number of years, and that really it affords us a large mobile power asset, and so that's going to be at the heart of all of this in the long term.
And since we are still a little ahead of schedule, I do have one more question I do want to ask you, and that is, how did you form your team?
Yeah, it's a good question. I think we're fortunate right now to be a growing company, thanks to NASA for that, and as well as our other customers. We have some really awesome people at our company that are seriously capable and have a lot of prior relevant experience. So we were fortunate to be able to reach out and leverage those skill sets from across our lander team, from across our rover team, our R&D teams, and they all weighed in on this design. So we had a pool of about 140 people that we were able to leverage for this, and we picked those that were most interested and most qualified.
Fantastic. Okay, Kayla, if you're okay, I'm going to move on to the next team.
Let's do it. That sounds great.
Okay, great. Thank you. So the next team is Planetary Surface Technology Development Lab. And this is for mission activity 2, where they did power from the power plant to a water extraction plant that was inside the crater. And Paul and Marcelo, I'm not sure if you're going to split this, but go ahead.
All right, thank you, Darren. I'll start it off here. So we're the Planetary Surface Technology Development Lab team, and we have named our solution the Wired Watts Whenever and Wherever You Want, or W5. So like I said, we have a group of students that work on this particular competition. So they're listed here. Marcello is the representative right now of that. So next slide, please. And so we've come up with a technology that kind of uses the environment to our advantage in a way, right? So the key here is to get the power from the lander. We just have pictured Eclipse lander, but it could be a VSAT or something else that was brought there by other companies. And so our rover would then deploy either already connected to that power system, but it could also plug in as necessary, connect to it, and then drive while deploying a cable to, in this case, the ice processing facility as shown here. And so we've leveraged 2 other companies that we have collaborated with in our previous work. And one of those companies produces a superconducting tape, essentially, mostly for Earth applications. But we decided that was a great technology to leverage in the permanently shaded regions where it's really super cold all the time. And that cold allows that cable to operate at superconducting properties, basically. And that allows us to have a really, really thin tape cable, essentially, that allows us to transfer almost 3% of the power from where it's generated down to the ice processing facility. The nice thing about superconduction is that you don't lose any energy, basically, because it has 0 resistance. And so we're leveraging that for the power use here, but you could also use that for communication and other purposes. Now, the other company we worked with, Space Application Services, has a technology called hot dock that we also leverage. And so that technology allows us then to dock with the other systems. And so that could be, in this case, an ice plant, but it could also be another rover or some other system that has a similar kind of docking mechanism. Now, the way it works, you can see on the right, we have the landing and egress from the Eclipse lander. Then we deploy first a sort of conventional cable almost, although we have made our own special flat tape as well, which is not superconducting. In this case, it's copper-based. We traded a lot of different materials, and copper turned out to be the best mass-wise and energy efficient-wise. Then once you reach the darker area, we start descending into that, and we deploy our superconducting tether for that particular section. Now, depending on where you are, you might be all in sunlight, or you might be all in the shade, or you might have partially shade, partially sunlight. And so we looked at all these different alternatives, and you can see that in the table that even in the worst condition, we can still get up to about 81% of the power generated to the plant in this case. Next slide. The details of this basically is that we wanted to really use the environment to our advantage. And so we created that flat tape conductor. We created the spools for a NASA Big Idea competition. And we leveraged that technology that we had developed and applied it to this particular problem. And then you can see at the bottom right here is our vehicle that we designed to go down up to 45-degree slopes using while unspooling this tether behind it, basically. And so we did an iterative approach with all of these different things. We tried some things out. Sometimes they worked, sometimes they didn't. And then we improved the system and we came out with something that worked surprisingly well. But as you can see from the numbers, some really nice efficiencies. Marcello, did you want to add anything?
No, you did a very good coverage on our system.
Good. I guess I've been paying attention.
That's good to hear.
Open to questions if there are any.
I have a couple. First, you talked a little bit about the way you use that harsh environment to actually to your favor, right? Especially the cold in it. Could you talk a little bit more about what inspired your solution?
That's a great question. Well, actually, it's for me at least, it's an old idea because I actually used this in 2001 during my master's thesis to get power into a crater where I had designed a lunar telescope that also used the cold to its advantage to passively cool an infrared telescope. And so, again, the idea was to not fight the environment, but actually have it help you in this case. And so if you can use superconducting, which only happens below certain temperatures, then suddenly you get zero resistance. And that means that you can make things much lighter. You can transfer a huge amount of power to very small cables and virtually zero losses. So it's really, really beneficial for many different ways. And it was sort of like the perfect technology for this kind of an environment. Now, of course, the tricky part was that there is a sunlit part where you can't use that. And so one of the challenges that we had to overcome was how do you combine, that really perfect technology with sort of the non-perfect region that you may have to bridge. And Marcello and other students have done a great job in figuring out how to combine these different things together.
So what do you see as the next steps for this technology for you moving forward?
Well, the next step, I think, really is to test it under the relevant conditions. And so we have a dusty thermal vacuum chamber here. And so we've been working on continuing to develop the technology and really prove that it works under lunar conditions. And so our vacuum chamber will be sort of filled with a little dust to simulate the lunar surface. Basically, we'll put the cable on there, we'll make it cold, and then we're going to test the power transfer as well as the communication, because we can do both over that same cable. And then hopefully, we'd like to partner with some other companies to hopefully actually bring this to the lunar surface and demo it. So I'm not looking at Astrobotic there or other companies, but we're certainly interested in further developing this. So, and I'm sure Marcello doesn't mind working on this some more too, right? For your PhD.
Yeah, it's been pretty fun so far.
Excellent. Well, with that, what would you advise other people who are were considering participating in a challenge like this? Any recommendations?
I don't know, Marcello, what would be your most important recommendation from participating in this?
Well, I think a few items. Well, a good idea would be to start early on your proposal instead of starting later. Other things to do, find a good team that you'd like working with. It's really hard to do all this work alone. If you have a good team, you can get anything done.
Yeah, I agree. I think key for us in being successful is having a great team to work with. And so like Astrobotic, I had a big team to sort of choose from. We had 40 students working in my lab. And so we asked for volunteers and people with the right skill sets that we thought we'd need. And so we could put the best team together to get this done successfully in the time we had. And fortunately, we already had the lab set up, and we've done a lot of preliminary work to be able to jump into this and be successful in it. So
excellent. And just because I have to ask this, what difference does winning phase one mean for you and your team?
Well, first of all, it was extremely exciting to hear that we were indeed picked as a grand prize winner. Well, it's a validation of our effort, right? So we've been building this lab, and we had this idea that we could do this, and so winning, first of all, was a validation that yes, indeed, we can do this as a university lab. But second of all, I think one of the things the prize allows us to do especially is to further develop it. And so, hardware costs money. And so it's very helpful to have some money to be able to do the test and buy new hardware that allows to get to that next step, basically, and make it more likely that we can achieve going to the lunar surface.
Okay. Well, thank you very much. Let's start moving on then to the next team, to the last one, SkyCorp. So first, this was the winner. SkyCorp was the winner of Mission Area 3, and Mission Area 3 was delivering power from the power plant to an oxygen-producing power plant, a pilot plant, I'm sorry, at the operating outside the crater this time. And so, Dennis, I'm going to hand it over to you.
Thank you very kindly. We did ours specifically because I don't like cold weather and thought that we would have more fun working with the Lunox plant. This is some of the stuff we've done here in the past here in our kind of a collage that we've put here. We worked on the Lunar Orbiter Image Recovery Project, recovering images from the 1960s. We had a place we call McMoon at NASA Ames. We've done a lot of work with NASA on lunar base design, and down there in the lower left is actually a 6 kilowatt solar and wind trailer that we used with NASA at the Desert Rats in 2009 and 2010, where we actually provided power to the habitation that you see over there in the left. We combined with a power system from Glenn seamlessly, and we were able to actually also charge the NASA Surface Exploration Rover and the Athlete. So we have a bit of experience in this level, in this area. Next chart, please, sir. Yeah, and oh, by the way, just our team members, Kyle and Mark, are both, we have a NASA Phase 2 safety that is due today. Inputs, we're actually flying part of the hardware that is in our scenario here. It's called the Intelligent Space System Interface. It's from a German company that we're partnered with called IBOS GmbH. It's technology that came out of the German Space Agency DLR for transferring power. We can transfer up to 5 kilowatts with a single ISSI, along with a gigabit Ethernet and optically coupled, and also CAN bus. So we have control, we have high-speed data, as well as electrical power. And we'll be flying now. We deliver hardware September 24th for flight to the space station in December on SpaceX 24, where we'll be doing a 6-month flight qualification of the hardware for data and power transfer on the Kibo module outside the space station. And so we took some work that we've also done with NASA Langley in the past. You see, we call it a power lander there. And so we use that for the NASA baseline for what we're providing power with. We have a little robonaut that we also developed along with some work we did with NASA on large space structures and several years ago with a Segway type vehicle to where the robonaut can actually plug in our power cable. And we did an extensive analysis pertaining to the power cables on AC or DC. And it turns out, and I think this will be the case on the moon as we go forward, we're going to probably end up with AC power distribution just because of the same reason Tesla beat out Edison. AC is more efficient over a longer distance, although we were able over 100 meters to have a 97% power transfer, even at 120 volts DC. We kicked it up to 480 volts, 3-phase, and we were able to go a kilometer at about 98% efficient. So we had a lot of fun with that, and some of this leverages off of work that we're doing right now. We have a solar-only power trailer sitting at Yellowstone National Park that's now been operating for 10 years, providing power with a long power cable to an entire ranger station at Beckler park. So what you see here, this is an older NASA design. This is called LOTRAN from the Space Exploration Initiative era. It is a human and autonomous robotic rover. It has exceptional capabilities, and about $20 million was poured into this back in the day. So next chart, please, sir. What we have here, we show our VSAT kind of design here based off of the LOTRAN trailer, as well as our 106-foot tower that we've actually already built and deployed. And some of these are, we have power generation systems in Wyoming and Colorado for the oil and gas fields terrestrially. So this is our terrestrial application implementation. And so these are used in many areas along with our solar only system at Beckler Ranger Station. It's already an 11 kilowatt system at 8,000 feet. And so we just string the cable out, and then we have our handy dandy RoboNaut that makes the connection to this right here is a vacuum induction furnace that would be used to make Lunox. And it's our feeling that with NASA going with the Starship, that lunar oxygen, which makes up 2/3 by mass of the payload or the mass of the Starship landing on the moon, will be invaluable going forward in the near term for providing lunar oxygen to help support Starship flight operations. So thank you very much. Your questions. Can't hear you.
Just unmute there real quick. Yep, no, my apologies. Let me just so I'm curious, why did you decide actually to participate in the Watts on the Moon Centennial Challenge?
Well, one is that we missed the VSAT deadline by about 10 minutes because of our wonderful Inspires website at NASA. And we've worked this issue. Again, we've recharged the NASA rover at the Rock Yard at JSC. We have delivered power at Desert Rats. So this is something we're exceptionally familiar with in generating and providing power from both mobile and fixed platforms, both DC and AC. So it's something that we knew we could do. We had our team here, and we have the hardware to move forward, because what we're doing right now with the ISSIs is going to be an in-space power transfer system to where we can transfer power from payloads to spacecraft for large space structures, on-orbit assembly. And so there's a whole plethora of applications. We're sponsored by the Defense Innovation Unit. We're also sponsored by other entities in the Defense Department, and deploying standardized systems. And this is something I've worked on for over 30 years, is deploying standardized systems in space. And now the time is finally here. After the third time of not making it back to the moon, I think we're going this time.
Fantastic. Okay, and what do you see as your real next steps for the technology? What do we got to do next?
Well, we've got our flight effort that's going up this year. We'll be monitoring it outside the space station for a full TRL-7 qualification. The same thing for our avionics. We even have, we're using a space station has a really cool new means to connect to payloads called KUIP. And we're working with VentSurf at Google for the interplanetary internet protocol that will allow us to teleoperate on the surface of the moon. We're going to be building the entire hardware suite that we need. We already have a trailer with a 106-foot tower. We can show that deployed. We also were just awarded for a 100-volt DC solar array that we're moving into flight qualification on beginning in about 30 days. And so we basically have all the elements that we need to go forward to demonstrate the Watts on the Moon scenario.
Perfect. So, and what do you think are the biggest challenges you face in coming up with your solution?
The biggest challenge has, it's almost never technical. It's always organizational and financial, and being able to have the resources to do this. So we did all of our previous work with NASA on our own dime during the vision for space exploration. It didn't really go anywhere, but we worked with NASA, and so let's call it cultural. You know, we've been working on this a long time. Those of us who have gray hairs have been through this, the Space Exploration Initiative, the Vision for Space Exploration, but this time we're going to go. And so that's the biggest issue, is making the decision and sticking to it. And I have to give both the Biden administration and Administrator Nelson kudos for not completely changing course and for maintaining the course for getting to the moon, to where all these young people here that by the time that they have our gray hairs, they might be living on the moon or even Mars. And that's something that, you know, when I was a student in the late 1980s, that is something I anticipated, but I really think these guys will have the chance to do so. And that gives me hope, and that makes us want to make this happen.
Hmm. And so to wrap it maybe all together, kind of this answers to the cumulative answer about what you see as the biggest benefit of your particular technology in this mission space.
The industrialization of the moon is the key to the future of humanity. The industrialization of the moon enables the settlement of Mars. And the settlement of Mars and the industrialization of the moon are key technologies in the 21st century that will make the 21st century more prosperous than we ever dreamed in the 20th century. And I think it's a goal that we all want to have. And I think it is a goal that will help us get beyond our, let's call it, our current age of chaos today.
Wow. And that's a beautiful way to close out, I think, this Winners Roundtable. Thank you very much, all of you. Back to you, Kyla.
Great. Thank you so much, Darren. I really appreciate it. And a big thank you to all the teams on behalf of HeroX, NASA, the judging panel. We're so thrilled to have your participation here with us, and really excited to be in this with you. I'd like to just ask a few questions of Denise and Darren before we close up today. Denise, for you, today we heard from 3 teams that have ongoing space technology efforts, but you know, the 3 of us who looked at the entries know that not all teams came with that background. In fact, there were some very competitive teams who have not previously worked with NASA. What would you say to teams that don't have the same depth of experience working directly with NASA that might be interested in participating in phase 2 or in another NASA challenge?
Yeah, Kyla, that's a great question. Thank you. So one of the reasons we do the crowdsourcing is to access everyone. So this, of course, is a U.S. competition. So you have those rules to be a U.S. citizen or have your green card, but we want everyone to come, whether you have experience with NASA or not. Don't be discouraged if you don't. Like Kyla said, we saw some great concepts that had no previous work with NASA at all. So we welcome everyone to come and take part of phase 2 in the fall when we open it. You don't have to be part of phase 1 to compete in phase 2. And I'll talk a little bit more about phase 2 in a minute, but that prize pot is $4.5 million. So a lot more than phase 1. So please come and bring us your ideas. And yeah, we'd love to have you. Thanks, Kyla.
Thanks, Denise. That's actually a really great segue to talk about phase 2. Could you share with us a little bit about what teams can expect for phase 2? You're on mute.
Sorry about that. So phase 2 is currently under development. We expect to launch it in late October, early to mid-November of 2021. It'll last a little over 2 years. We're saying about 28 months. Like phase 1, phase 2 is going to focus on the 2 NASA technology gaps we have. So it'll be energy storage and power distribution for this phase, and then do some testing and evaluation. And we're hoping right now that you will have 3 progressive levels that you'll advance through. So we'll have level 1, level 2, and level 3. We'll have a total prize purse of $4.5 million. And we're currently planning on 2 milestone awards, like for level 1 and level 2, and then the grand prize purse at the end. So that's the current plan for phase 2. So you should see the announcement on the HeroX website. So please follow that closely. And everyone, please join us for phase 2. We're looking forward to seeing what you have.
Great. Thank you so much, Denise. Darren, you come from the Department of Energy. So, the solutions proposed by these teams have the potential to support a sustained human presence on the moon. But we all know energy storage and distribution is also important here on Earth as well. How do you see these types of technologies being applied in a terrestrial setting, and what might the impact of some of these solutions be?
That's a really good question, and it's actually why I'm here. So first, I think they can have a very meaningful impact, no question about that. But it's not just the technologies, though they're an enabler and make it all possible. Proving out the feasibility and robustness of these integrated systems that you're working on right here is as equal a piece, because once they're proven out and shown to be robust, then that's when really we can get some traction here on Earth as well, here terrestrially as well. And I think in the nearer term, and I'm not going to define what nearer means, by the way, what I see the huge potential for these are in the area of disaster relief. I mean, there are lots of other areas as well, but that one comes to mind to me probably mostly because of what happened in Puerto Rico in 2017 with Hurricane Maria. DOE and a lot of other agencies were heavily involved in that. We saw a lot of what was going on. Someone actually at my office went down there as well. And so, as you all probably remember, that storm absolutely wiped out the infrastructure there. It did a whole lot of other damage too, but it certainly wiped out the electric infrastructure. And though a lot of the central power stations came back online relatively quickly, there was no way to transmit the energy. So you certainly could see some of the work that's being done here proposed by these teams in beaming and how you target beams and all the other pieces that go around that could be of real value in situations like that, where you have power plants that run 50 miles away. You have towns and municipalities that can't get power. And so this could be really, really helpful in that way. One of the things that happened that was really bad, obviously, is you lose power. You lose all your water purification, your sewer, all your other utilities. And so being able to beam power effectively to these very different areas could cut down the time and the suffering and all that, and footprint, by the way, the CO2 footprint for that matter, dramatically. I mean, there were 6 months after that storm, there were still areas without power. And that's something we've got to not let happen again. So disaster relief is certainly one of them, or that's one type of disaster relief. There's also others, if I can just take a couple more minutes here. Other things that are extensions of what are being done here. You heard SkyCorp talk about, hey, we want to move this to Mars habitation and being able to do a lot more with these types of technologies. And that's true on Earth too, right? So if you have an epidemic that breaks out somewhere, right now it takes a lot of energy to get a lot of people in there to build hospitals and do all these kinds of things that you need to do, water treatment facilities, all the stuff you need to do to be able to serve the people who need it badly. Having these more autonomous kind of systems that can set these things up so you can envision there's a disaster, you have a couple of C-130 cargo planes go there, drop off some of these self-assembling kind of systems that can build the shelters, put the power in place, put the microgrid in place, start powering some things similar to what you're doing on the moon, could be enormously helpful. And then when you get the people there, there's already something set up for them and they can get moving quickly. So there's a whole host of things in this area, like with hazard remediation, et cetera, and all those kinds of things where these kinds of autonomous technologies could really, really be powerful.
Thank you for sharing that, Darren. It's so amazing to think about the potential impact of these types of solutions, right? Not only are they allowing hopefully a sustained human presence on the moon, for us to go to the moon and stay, but also to be able to contribute to disaster relief and other Earth applications. The example of not having power 6 months after a storm is just heartbreaking, and having something like this be able to make a difference should that happen again is a really great goal to strive for. We're getting to the close of our webinar. I wanted to ask you, Darren, do you have any final remarks that you'd like to share today?
Yeah, there's a couple of things. One, a big thank you to everybody, including you, Kyla, as well as NASA and all the people who put into this. The winners, of course, but a lot of the other folks I want to give a shout out to me. It was very competitive, right? And we only had a limited number of things we could do in this, but there were a lot of great ideas that came in that did not get awarded this round. We need all the ideas we can get. We need all the diversity we can possibly get. So I'd certainly urge people not to get frustrated if they didn't, for some reason, get awarded this time, and to keep looking for the next rounds and the other solicitations that may come out, because we need your ideas. And so I certainly want to give a shout out to that. The other thing I want to highlight is something Denise was talking about, and you were too, Kyla, is the importance of phase 2. The ideas are great, but we need to make sure that which in phase 2 will happen, to get the hardware built, get the demonstration proof of concept going, because that's really where we need to go afterwards. So I'm hoping everyone keep your eyes open for the details from phase 2 when they come out, and I hope if you're able, you folks go in and put into that phase 2.
Great, thank you so much, Darren. Denise, anything that you would like to add?
Yeah, as Darren said, thanks to everyone. This was a lot of hard work. We recognized that when we looked at the proposals and all the work that was put into it. And also, we are going to provide feedback. I saw that in his chat a minute ago, but the feedback will be generic to all teams, just some things that we noticed that were repetitive with the solutions that we looked at. So just watch the HeroX website for that, and you'll get that generic feedback. It'll go to all teams. So please read that. A couple of things we noticed happen through many of the concepts that we got. So we'll do that shortly. And thanks again, everyone.
Great. Thank you so much, Denise. And with that, we are coming to the close of our discussion today. I would encourage you all to go follow the challenge on HeroX.com. I've put the link in the chat, but it's also HeroX.com/WattsOnTheMoon. And if you click the follow button there, you'll be notified as we have developments and announcements regarding phase 2. That's the best place to go. If you already participated in phase 1 or you already signed up, you are already subscribed for that. So don't worry about it. We've got you in our list to make sure you know about phase 2. There are also other NASA challenges that are always launching and other opportunities. So I do encourage you to go and check out those as well. To all of our guests and attendees, thank you so much for taking your time out of your busy day to hear about these winners' solutions and to help us celebrate them and their accomplishments. For everyone that submitted, I'd like to echo what Darren and Denise said. Thank you for your submissions. It truly was a very difficult process to select the winners for this challenge. And I would really like to encourage you to all consider phase 2 when it comes around. It is open to everyone, and we're looking forward to hearing all of your ideas. And with that, thank you so much for taking the time. Depending where you are in this big wide world of ours, have a wonderful morning, afternoon, or evening. Thank you so much, everyone.